I don't have very much time today because I only have 52 minutes of time on my camera.
We'll cut them off.
So we're going to have to get this done within 52 minutes. Today we're going to start putting some things together, and this is kind of where we get the benefit of covering material for two classes at the same time, because we're going to talk about material that's important in our 126 semiconductor class and also important in our 140 controls class. And that is the idea of taking AC, which is natural. AC is natural because it involves a circle, and the rotations are natural in our universe. The Earth goes around in a circle. Everything goes around in a circle. The motors and generators all go around in a circle. And we need to convert that somehow to a straight line, which is the way we represent DC. Okay, DC is not natural. DC is something that we have to manufacture generally. We can get it from the sun. We can get it from batteries, which we need to charge. But the preponderance of DC comes from a device that converts AC to DC. And in order to do that, we're going to use a setup that looks like this. You guys will be using these to do your labs. You'll notice it has a transformer on it. So a transformer is going to be part of what we're going to be playing with, and we did some of that last quarter in our 128 class. So we should be ready to start. What we are actually going to talk about is called a DC power supply. Okay? A DC power supply starts out with our line voltage, our 120 volts, 60 hertz, goes through a transformer, goes through a rectifier, goes through a filter, and we talked about those last quarter also, out to our load. And that is the basic, very basic block diagram of a DC power supply, and we're going to look at all of its component parts. The beauty of it is, we've already looked at all three of them. We just don't know it yet. Okay, so let's take these blocks and let's kind of draw them out in terms of the schematics and the symbols that we would normally use to represent them. A transformer looks like this. And we are going to make this 15 or so. We'll make it 15 to 1. Okay, and since what we want is DC out, what we're going to use as a filter is a capacitor to ground across the load. That makes this a low-pass filter. All the high frequencies go through the cap to ground, giving us only the low frequencies here. We've seen this before. The ultimate in low frequencies, of course, being DC with a frequency of 0. Okay, so filter, check. We've got a filter. Transformer, check. We have a transformer. The one thing missing is the one thing in the middle. which is the rectifier. What is rectifier? What does rectify mean?
Something that changes.
Nope. So when I say, for example, how are we going to rectify that situation?
No, correct it.
Correct is one way to look at it.
Fix it, refine it.
Fix it, refine it. But that's really not what it means.
Convert.
Smooth out.
Smooth out is one way.
To get the part out that we want.
I don't know if you, here, let me give you an example. You know, an education is a good thing. Let's talk about snakes for a minute. You like snakes?
I do,
Nope.
actually.
Snakes move in two different ways. Snakes either move this way by squiggling their bodies. That's the way we normally see. As a matter of fact, we refer to that as serpentine motion because it's the way serpents move. But if you watch the big boa constrictors and pythons, they don't move like that. They move like caterpillars. They take the ribs that are in their bodies and they move the scales on their bellies, and they actually move in a straight line. Boa constrictors and pythons move in a straight line, and we call that rectilinear motion. Rectilinear. Which means in a straight line. Okay, so when we talk about to rectify something, normally what that means is to straighten it out. We need to get this straightened out. Rectify means to straighten out. And that means we're no longer going to have current flowing in both directions. We're only going to have current flowing in one direction. So our rectifier is just going to be a diode. I've got kind of a mishmash of parts here that we need to put together into an actual circuit, and I'm going to go ahead and do that now. We have all three of our parts, our transformer, our rectifier, and I'll do it in blue. Our filter, and our DC output voltage. Okay, so coming in here, we have 120 volts at 60 hertz. We said that was equal to 170 volts peak, roughly, right? Isn't that what we came up with?
Yeah, I think it was. It was like 169.8 or some bizarre thing like
Yeah, somewhere close to that. And if I have 170 volts peak here with a 15 to 1, I take 170 and divide it by 15, and that gives me 11.3 volts. At the output of my transformer. Okay, so right here, what we're going to see if we look at the voltage there, we're going to see 11.3 volts peak and minus 11.3 volts peak. That's what we'll have right there. Then it goes through the diode, and what does the diode do?
Takes only the top portion.
This is blocked by the diode. So the only thing it can get through, I'll put another loop here just to indicate what we've got. All the bottom ones get blocked because that requires the current flow in the other direction. The diode only allows it to flow in one direction, right?
Mm-hmm.
So we're doing the Humpty Hump thing on the outside of the diode. We just have a bunch of humps. Sequence of 11.3 volts humps. And actually, that voltage is not right. It's actually going to be
Drop 5.7.
10.6 volts. Because plus minus 0.7 across our diode. Remember, our diode doesn't do its work for free either. Okay, now watch what happens here with our capacitor. Coming off the diode, we have something that looks like this. Cecil to C6 C serpent. But what does our capacitor do? Well, our capacitor charges here and then discharges here. Charges back up, discharges. Charges back up. And where does it discharge? It discharges through whatever we have connected up to it. Whatever load resistance we have connected up to it is what it discharges through. Based on an RC time constant here. Okay, you have an RC time constant. The capacitor charges up from the source, and once the source goes away, it discharges through the resistor. And as it discharges, of course, it loses some of its voltage. Okay, after a certain amount of time, it gets another issue of power from the source, charges it back up, and then it discharges. Perks back up and then discharges. Perks back up and then discharges. Never gets down to zero because it doesn't discharge fast enough to get down to zero before it gets another. It's kind of like the way my paycheck happens. This happens every 2 weeks. Then I spend. As long as I don't get to zero, doing good. Right, every 2 weeks I get a new paycheck and I got more money again. And then spend, new paycheck. See how that works? Happens everywhere. So what we end up with, taking a bunch of this stuff away, is this. 0 volts. And I end up with something that looks like this. Where that's my capacitor charging and discharging. That's going to give me a DC voltage and an error voltage or a ripple voltage. And voila, I now have DC. green one here. If I add another capacitor to my circuit, that makes this fall down less each time and gives me a more stable DC voltage, reduces the amount of ripple by having more capacitance and holding that charge just a little bit longer. So in theory, we could continue to add capacitors here, and every time we add capacitors here, that line will get smoother, won't it? You see why that is? Mm-hmm. But every time we add capacitors, and sometimes we are talking about capacitors, not little dinky ones. Every time we add capacitors, what are we doing?
As in like adding money, weight.
Adding weight, adding size, adding money.
And adding heat.
And probably, yeah, there's probably that too. But so we got to be careful. We can't just willy-nilly add as many caps as we want. If this is supposed to be a power supply that goes on a drone, for example, I just decreased my payload possibly to 0 because I had to add another capacitor to smooth out my voltage. Okay, so there are other ways to do that, and we'll see what those other ways are as we work our way through this. One thing that we can do is put a zener in here and set that zener at, say, 9 volts. If I put a 9 volt zener in there, basically at that point I'm sending everything above that 9 volt level through the zener, and that will give me a fairly straight 9 volts at my output. That way I don't need a 9 volt battery. I can use this as a battery substitute. So I can use a zener. We'll see that a little bit later because there's, you know, we did draw up a block diagram, but there are other more complex block diagrams for a power supply. This is just really the very basic, simplest possible power supply that we can come up with is a single diode as a rectifier, a single or group of capacitors. And remember, if we have 2 capacitors, we simply add them together to get the total as a filter, and a simple transformer to get our voltage into the ballpark. Our transformer gets us in the ballpark. We always want it to be a little bit high because we know we're going to lose a little bit of voltage with our diode. We might lose a little bit of voltage with our caps and stuff. So you always want to start out a little bit higher. Now if really that concerned about it, I can use a variable transformer that uses a core that you can screw in and screw out that subtly adjusts the turns ratio. Okay? So this particular power supply has a name. It's called a half wave supply. It's the cheapest and the worst in terms of quality DC. Oh, come on, Don, you know you want to. There we go. Mr. Harris, do you have any questions on what we've discussed at this point?
Mm-hmm. Nope.
Dawn?
Okay, why is it the worst in terms of quality?
Here's why.
Is it because the ripple effect is wider, or is it because there is a ripple effect versus a nice clean? I mean, what make you, you're calling it the worst in terms of quality, what makes it?
All right, let's look at this for a second. It's the worst in terms of quality because we haven't looked at anything better.
Oh,
So that's,
okay.
that's why you have a question. Because we haven't looked at anything better yet.
Yeah, because I know there's got to be a way to clean it up.
So when we look at a half wave, what we see is this. Eight milliseconds, 8 milliseconds, 8 milliseconds, 8 milliseconds, 8 milliseconds. Actually, what, 8.6 or something like that, 8.3. Because roughly 60 hertz, right? 60 hertz is 16.6 milliseconds. So roughly 8.3 milliseconds or so for each part of that waveform. And of course, we're getting ready to get rid of the lower part. So I have basically 8 milliseconds of power, 8 milliseconds of nothing. 8 milliseconds of power, 8 milliseconds of nothing. So I'm really wasting half of the waveform. And my capacitor has to stay charged for 8 milliseconds. That's a long time. Now tomorrow or next week or whenever we all decide to meet up together, we're going to add a diode to our power supply and make a few other changes, and we're going to end up with something like this, where we're going to use both halves of the waveform, 8 milliseconds, 8 milliseconds, 8 milliseconds, 8 milliseconds, like so. And now, if I can do that, now look at what my cap only gets to discharge for a short time. Which means you're going to end up with a smaller amount of ripple because the cap is getting charged twice as often now. Okay, full wave requires a better transformer, more diodes, and I'll say a better transformer and or more diodes to get the job done. Okay? That's why I refer to half wave as being the worst, because there's such a huge gap between energy bursts, if you will, that the capacitor basically has to supply all the power to a load. So in a sense, if you really wanted to look at it another way, what we're really doing is charging up a battery. A capacitor and a battery are very similar. Charging up a battery, discharging that battery. Charging up the battery, discharging that battery. And every time we discharge that battery, voltage goes down. Okay? With a full wave, you're not waiting that whole period of time. You're getting charged again at the midpoint. So it doesn't get a chance to fall as far as it does in the half wave. But the full wave also costs you more money and takes up more space. And costs you more in terms of diode bias voltage. Does that answer your question, Dawn?
Mm-hmm.
Does that make sense?
I could really get them and go, so what makes a better quality transformer?
What's that? What makes a better quality transformer is, in this case, what we're going to need is we're going to need a transformer that has a center tap. Okay, so it's going to be a little bit more expensive of a transformer to make that work. Okay? We can get rid of the transformer with the center tap, but if we do that, then we're going to have to use 2 more diodes, which is going to reduce our output voltage by another 0.7 of a volt. So either way, there's a cost to everything positive. As you know, once you become adult, you realize that nothing good ever happens without a negative something to go along with it, right? Mm-hmm. Every time somebody brings me a plate full of money, there's some bill that shows up in the mail that I didn't think about, like, got a $500 tax return. Ha ha ha! You need new brakes. Didn't pass inspection, right? There's always a handout ready to take any benefit. It's the same here. There's always a negative side. But the beauty of electronics is we know what those negative sides are going to be in most cases, and we can plan for them. All right, questions at this point? Next week, we will look at 2 types, not just 1, but 2 types of full wave power supplies. We have a full wave that uses a center tap, and a full wave that does not use a center tap, but uses 2 extra diodes. And we will discuss those next week, and then we will compare the 3 different power supply types that we are going to look at, and then you will build them using these boards that we have. You guys will, there's your transformer, there's your connections to the transformer. We have a fuse there in case you screw up, so there's nothing to worry about there.
Stock.
What's that?
Lots of them in stock.
Yeah, we have plenty of fuses, so we should be in good shape, ready to build some power
We're not
supplies.
blowing stuff up and burning stuff we're not learning.
That's right.
If you're not burning, you're not learning, right?
Yep.
Yeah.
You gotta
There
learn
you
from
go.
your mistakes.
All right, there's more than a few of these things that have black marks on them for when people put in a diode and put it in backwards or something. Yes, things do happen. But better here than when your boss is watching, right? Okay, that's all I have for today in 126.